Okay, so let me share my screen and we will start. Okay, so today is the last lecture of my mini course, which is devoted to point processes for interacting particles. And today I want to discuss some ideas of systems with coalescence and annihilations. So on the first lecture, I give you two main examples that in which we are interested in, and first of them we discussed yesterday. This was the examples of systems of bosons and fermions, and we say that they describe systems of particles with attraction or with repelling. But today we will do something different. Today we will consider a system that have the description in terms of family of Brownian particles, and then we will see that we can investigate this system using point processes. So to describe the model, I will just use this non-formal description. So let us start from finite number of points on real line. So I fix n points, so that they are from R each coordinate, and from these points I will start Brownian motions. So W with two indexes here, X denotes initial value and T corresponds to time. So this family of Brownian motions, we assume that it has the following properties. So as I said, the initial value, so at time 0, the value is xi, and the particles move independently before they meet one another. I don't want to get detailed for definition, but one can give a rigorous description for this property. And their last and most important property for us is that we want to describe the behavior of these particles after they meet. So we will consider here two cases when they coalesce after meeting and form one particle which will continue behavior of Brownian motion. And another possibility is that they annihilate. This means that if they meet, they just vanish after meeting. One can imagine how plots looks like. So if in the case of Brownian motion with coalescing, you can see that I draw trajectories that move somehow independently before they meet, and after meeting, they coalesce and continue as one trajectory. In the case of Brownian motion with annihilation, we just kill those particles who meet, and we will have this picture. So now, what is the main question of investigation of such families is that we want to know the position, location of points at fixed time t. We want to know asymptotic for small t, for big T of such number of points in our system. And for this, of course, since we study point processes, we can define a point process which count a number of particles in such systems. So here I will denote by x with index C or with index A. So this is the case of coalescing or annihilating Brownian motion that starts from points xi. So here this index means subset of real line, and actually later we will see that we can start from any points, like from all points of the line. But for now, like I define finite number of Brownian motions. So here I write just initial location of Brownian motions. Okay, so then I define a point process correspondingly for coalescing and annihilated Brownian motion. Here I will use notation C or A, depending on what kind of system we will consider. So by this notation, I count number of points in this system that are located in subset delta. So in such way, I can define a point process. So what kind of properties we can get from such definition of a point process? Let us consider, for example, case of coalescing Brownian motions. So, like if I want to calculate expected value of number of points in my system. So how I can rewrite, how I can count number of points that are left in my system up to time t small. To do that, we can slightly rewrite. We can understand how we can count the number of trajectories that survive in time t small. For this, I will define following stopping times. So I will consider a finite horizon of time t capital, and I will define t tau first to be equal to t capital. Next, I will define next stopping time tau2 to be equal to the first moment when trajectory x that started from x2 meet the trajectory that started from x1. So here on this picture, like trajectory of that started from x1, here is a lower one, and then next trajectory x2. So here I didn't write. I assume that all points located in decreasing order. So I write this at like on my picture just described. So if we start from point x2, we at some moment we meet trajectory x1, and this will be my random moment of time tau2. And so on, tau3 I define as first moment of time when trajectory started from x3 meet a trajectory that starts from x2. Now trajectory from x2, this one, and here tau 3 we can see here. And so on, we define stopping times of a such way. We just want to know when trajectory with index xn meet trajectory with the previous index xn minus 1. So on this picture, you can see for better understanding. And now how I can count the number of trajectories at point t, at moment t. So I can count them as follows. Okay, x1 trajectory that starts from x1, like here it varies in any case because tau 1 is equal to t capital, so it will cross their moment time t. Now, trajectory that started from x2, it meets trajectory x1, and we do not need to count it. So we do not count this trajectory because it's stopping time less than t. For the case of trajectory x that starts from x3, we will count it because it met the previous trajectory, lower trajectory at a moment that is bigger than tau, so we count it. So with this understanding, we can count number of points in our system, just counting the indicators of events that tau I is greater or equal than t. So you can see here we count exactly 3 trajectories for which stopping times or meeting times is bigger than t small. Okay, so now if we rewrite it in such notation, we can understand how we can calculate mean value of number of particles in our system. So here I write the expected value. Here I write indexes, sub-index for expectation. This means that we start our system from points xi. And the point process here I denote by nt, and I just count all particles that survived here. And from the previous representation here, as you see, we just put expectation inside the this sum, so we have the sum of probabilities. Sum of probabilities that tau I is greater or equal than t. And well, one can calculate these probabilities. Why? Because, as I said, we consider our trajectories to be independent before meeting. So before meeting, we have just independent Brownian motions. So this is a nice problem for students about properties of Brownian motion. You can check that you can use actually the density of Wiener process at point t over 2. So these probabilities, actually, you can maybe not calculate precisely, but you can write an estimation, and you can get the expected value for number of points that survive at for time t. Now, the idea is the following. I want to start from our Brownian motion from every point of the line. So here there is some technical procedure that allows to do that. So you need to rigorously define a system of Brownian motions that start from each point of line. You need to define the joint behavior of this processes, but one can understand, like, if you consider approximation of the form that you just add more points, like for example, you can consider all rational, like numbers. You can start from 0, 1, for example, then you add 1/2 and so on, 1/4. You can do such procedure by adding more points, and of such approximation you can get a family that start from every point of the line, and of course, like, they two Brownian motions that start too close, like very close one to another, they will be almost immediately meet one another, and they will coalesce and form one trajectory, one particle. So due to this, from this we can get the expected value of points that you can find in some interval 0u. So here at time t I fix interval 0u, and the number of particles is proportional to length of this interval. So this is a very interesting result, and from it you can immediately get some understanding about number of particles around 0. So if t is 0, it tends to 0, you can see that the average number of particles in interval tends to infinity as 1/√t. The same if you will have t is not big enough, you will see that expected value of number of particles on the interval tends to 0 as 1/√t. So even if you know the asymptotic of such average number of points, is already like a good knowledge for us. Okay, so this is how we can just find the first characteristics. So you can here recognize the intensity measure of point process, you can see. Now, what we can do, how we can proceed with the next. I'm sorry, somehow 2 pages. Okay, now for the next question. On last lecture, we considered endpoint densities, and we saw how they connected to factorial moments or product moments of point processes. And this is the next step of investigation of a point process. And here I would like to discuss the results of the paper by Richard Tripe and Oleg Zaboronsky. Their paper is called the Pfaffian formula for one-dimensional coalescing and annihilating systems. So it's a paper of 2011. It's not so old, and they actually find out the formula for endpoint densities for coalescing systems and for annihilating systems. And they give her answer in terms of Pfeiffer of some matrix. So this is another algebraic structure for structure. So yesterday, if you remember, we considered point processes that had endpoint densities represented as as a determinant of some matrix or a permanent of some matrix. So here we have something new. So let us at first discuss what is this pfeif and how it arises and what is the definition of it. So for this, we will consider an antisymmetric matrix n by n. So this means that we have the following properties for its values. So this is antisymmetricity means, and for it is known, it's proved that for such matrix, for antisymmetric matrix, its determinant of a can be written as a square of some polynomial in the that depends on values of matrix of A, I, G. So this knowledge I write like this. So determinant is square of some polynomial. And this polynomial, in fact, is called a Pfeifian of matrix A. So Pfeifian is defined for antisymmetric matrix, and it has the following relationship with determinant. So you can say that Pfeifian is square root of determinant of a matrix. So let us consider examples of antisymmetric matrices. The very first example is 2 by 2, and it has the following form. So here, determinant of matrix A simply is equal to A square. I didn't write it. And so Pfeifian is equal to A. Now for matrix 3 by 3, you can see that you will have here a 0 because what you have antisymmetricity of matrix, so you will have sign of minus and plus. So all products will disappear. So for odd size antisymmetric matrix, Pfeifian is equal to 0. So this is important, and we will consider next Pfeifians of even dimension. Okay, so this is examples simple, and let us consider next example one more, because we will need it. My God, wait. So if we consider matrix of 4 by 4, you can calculate the determinant of such matrix, and you will see that you can represent it as square of such expression. So Pfeifian of matrix C is equal to this value, so you just add A times F minus B times E plus CD. So this kind of formula you get for four-dimensional matrix. Now you remember that you can calculate the determinant of a matrix using decomposition by row or by a column. So here also you can do the same. You can calculate the Pfaffian of matrix of dimension like 2n times 2n using Pfaffians of smaller submatrices. And the recursion for this case has the following form. So it's almost like for matrices. So we fix, for example, here we fix I, so we fix a row, and we will expand Pfaffian on this row. So how we do this? Again, we will sum with minus or plus the value. For example, I fix one row, and I will sum over all j that is not equal to I. So my summation will be over these columns, and here I will have three summands, for example. And here, Pfaffian of matrix Aij, here we cross the submatrix we cross lines and columns with index I and j. So for example, if here my I is equal, this is I is 3, j is equal to 1, I will cross these values, two of them, cross this. So I have this matrix dimension of, so each coordinate minus 2. So dimension of this submatrix now 2n minus 2 to n minus 2. Okay, so, and we do this for every columns. So you can check that you actually have this matrix, because for 2 by 2 we can calculate it easily. Okay, so this is how you can calculate the Pfaffian using recursion, and we will see that it's a helpful formula. Okay, so now when we understand what Pfaffian is, we can go in characterization of moments of Brownian systems with interaction. Sorry, here this line. Yes, this one. So now we will talk about the property of point processes that form by annihilating Brownian motions. And we will find a Pfaffian structure for such system. And to do this, we will start first not from endpoint densities, but we will start from such product measures or product moments. So this is slightly different from what we discussed yesterday, but here you can understand it easily what we have. So we have here the product of, I will define functions m with index t to power n that depends on points x1 and so on xn. This point corresponds to initial positions of the Brownian motion that we consider. And by definition, it's equal to expected value of annihilating Brownian motions. And here I use these symbols xit. This will be the list of all positions of particles that remain at time t. So I take the product of values of a function g here. Okay, so and now for this moments, Trapp and Zaboronsky in his paper, they write the Pfaffian formula. So it has the following form. You can see that if we consider 2n points, I'm sorry, here I should have write 2n 2n. We have 2n starting points, and to calculate it, we can use the Pfaffian matrix that is formed by the following functions. So these functions here we write just we write lower part of a matrix, no, upper part. We write 2n. So here indices where I is less than j, so we write this upper part of matrix ij, and the lower part of the matrix we just fill by antisymmetric properties. So we want this matrix to be antisymmetric, and here on diagonal zeros. So as you see, you just need to know how to calculate 2-point moments. So you just need to have a deal with these two Brownian motions with annihilation, and it's quite simple because you have the case when Brownian motion move independent, and after they meet they just disappear. So the system of two Brownian motion is quite simple to write all moments or formulas due to independency before meeting. And you can write the moments for bigger number of particles just in terms of 2-point motions. And this is quite interesting, and we can use this formula to get some more results. So how to do this? How they prove this result? They start with considering this function. So we have a function m that depends on time and space variable. So where do this space variable live? So we will consider ordered starting points x1, x2, and so on, xn. So we started from the point where they all are non-equal and ordered. And in this area, as I said, we have just independent Brownian motions. So if we start from 3 points before they meet, you can consider three trajectory of Brownian motion. So you have a deal with usual three-dimensional Brownian motion with independent coordinates. So this corresponds to three-dimensional Brownian motion. So we have, I draw such a picture. They start from a non-equal point and they somehow move. So each coordinate is independent until we this motion hit face of the following form. So where some coordinates are equal. So when we hit this, for example, this one where x is equal to j, we hit this one. So after this, what happened? These 2 points die. So if they meet one another, so they die. And we have now a deal with one-dimensional Brownian motion. Okay, so this is the case. But we here consider just even number of points. So I cannot draw a Brownian motion in four-dimensional space, but assume that we have like this. So, and then after two of trajectories meet one another and they die, we have a Brownian motion in space, in subspace V n minus 2. And now this Brownian motion live until this trajectory meet one another and they die. So they somehow you can say that the standard Brownian motion in dimension 2n, if we start from 2n points, they jump from space to space with lower dimension, just killing some of pairs that meet. So this is this idea is used to write a boundary value problem for this function, because we know how function behave in this open subset. And in this subset, the function mt just correspond to standard Brownian motion in space 2n, and what we have that function m will satisfy heat equation that is true for usual Brownian motion. So now here 0 infinity half line for time, and Vn is subspace for x coordinate. Now we need to specify boundary conditions, because we start and we live in subset Vn, and when we hit one of such faces, we have the following conditions. So of course, now we have two less trajectories, and here I denote which trajectory we cross out from the system. So we cross trajectory I and trajectory I plus 1. So from this, we get the boundary condition, and also we can have initial condition just from definition, because we defined it as expected value of position of points at time t, and we know that they start from xi each. So at initial time t, we have this value. And also note that at time 0, we can write this product as a phi-n of a such matrix. So you can try to do it by hands when our matrix is formed by product of such values. So you have here matrix dimension 2n by 2n if we start from 2n points. And you can see that the phi-n of such matrix is represented as just a product of each here g of xi. So what they do in paper, they just check that recursive that the phi-n that they write down here, not this phi-n that they write here, will satisfy this boundary value problem. Like for, of course, you need to consider a smooth function g in order for it to have a unique solution, and to check that M has a phi-n representation, they just check that phi-n satisfy this boundary value problem. And to check this, they use a recursive relation for phi-n that we discussed. And now we can see that the phi-n of such matrix is represented in this form. So you just need to check that if this terms will satisfy this boundary value problem. So this is the idea how they prove this result and how phi-n arise here. Okay, now I am sorry, I jump again over 2 slides. I don't know why it happened. Now I will not give you detailed proof, but in their paper they also obtain a representation of endpoint densities. I'm sorry. Densities for point processes. So I recall that we know from the last lecture we saw the connection between moments of point process and its endpoint densities. And since that they have the phi-n representation for moments, they get from that result phi-n representation for endpoint densities. And here I write the kernel of matrix for Brownian motion with coalescence. Okay, they get this formula that you can get the result for endpoint densities using phi-n of the following matrix. So this formula is quite big, I understand, and because for n is equal to 2, even you will have a matrix 4 by 4 because this kernel is a matrix itself. So, but you have a formula and you can use it in order to get some good properties for these systems. So, for example, let us understand if the points in a system of Brownian motion with coalescing, if they tend to repel or attract each other. And for this, I need to write the 2-point density. So I will use the Pfaffian representation. So it's not so easy even to write the explicit formula for 1 and 2-point motion. So what do we have? So here for one dimension, for 1-point motion, it's easy. Like we discussed, we find a intensity measure, and it has, from that you can get this density. Now for 2 points, for 2-point motions, the formula is much more bigger. So using a Pfaffian structure, one can write this formula for 2-point density. So I recall this means that this is a probability to find a particle in neighborhood of x and neighborhood of y. So we have 2 points, x and y. And here now we consider, I didn't mention, we consider Brownian motion that started from each point of the line. So we have a family that has very many trajectories at 0, but at the with follows of time, we behave something like this. So we want to find the density of probabilities. It is that here we have at fixed positions x and y, we have a particle from our system. So this is the answer for such case. And please notice that here we have this 1 plus, and actually we can represent this with this term. We can see that this is a product of one-dimensional, 1-point motion densities. And here I write plus some function g. This will be my function g. This one, I write it here. Okay, I forgot here pi 2, pi t. So this is my function g. And to understand if it is repelling or attracting our system, we just need to understand what is the sign of this function g. What is it? So it's easier from this definition. You can see that at 0 we have minus, minus some constant. And taking derivative, you can get that their function is decreasing on half line. And the limit at infinity, if you put here infinity, you will have 0 because of mostly of this exponent. It will kill this infinity. So you have this function g, something like this, such picture. So what does it mean? How we can analyze now joint behavior of 2 points in our system? So let us rewrite it. Let us rewrite in conditional probabilities as we did it before, or just from knowing that g is negative, one can get that the 2-point density is less than product of 1-point densities. And in terms of conditional densities, so here I use this informal notation that if I consider conditional density to observe a particle at neighborhood of point X, and if I know that in neighborhood of Y, I can observe one particle. So this is equal to just, if I will write from the first term, I will have just a probability that I can observe point at X and plus some term, and here G, function G is negative. So what we can say from this formula? Like, since it's negative, then if I know that I have one point observed here, then it's I will have so the conditional probability to find one point in neighborhood of close point X is smaller than if I don't observe at this point Y. So for close points where X and Y is close to zero, I recall that at zero G is negative. So for close points, they tend not to be close one to another. So they somehow repel one another. They cannot. So it's quite rare to see close points in our system. But of course, you need to take into consideration this time t. So now I fix time t. But if I fix 2 points, but I move time t, you can see that for bigger t, they repel more, but for smaller t, they don't repel. So this means that, of course, when you have time close to zero, you can find close points together. But for fixed time t, what we can say also for, if I consider distant points, so here to compare, I draw an interval 0, 1 to show that for close points we have repelling property, but for distant points, so if X and Y are quite far away, then you will have here almost zero, G is almost zero, and you will have that to find a point here or here on large distances is almost independent. So this how one can analyze property of such systems, known formula of endpoint densities, and you see you can say a lot just analyzing the 2-point densities and 1-point densities. Okay, and now also from the 5N representation of coalescing Brownian motions that starts from all real line, one can get the asymptotic of factorial moments. So because we have the connection between endpoint densities and factorial moments, you can just find the asymptotic, you can just integrate the density, and here of course to find an exact formula is quite difficult, but we can find an asymptotic behavior for example for small t. So what happened when everything just started? And it turns out that factorial moments is just asymptotically equal to usual power of u divided over square root of p times t. And from this, actually, we can get some limiting behavior of number of points in coalescing stochastic flow, and one can get in central limit theorem. So that's what we did in my joint paper with my colleague Fomichov. So we get the limit behavior for number of points on larger intervals. So here I count number of points that survive until time t, and they live in interval from 0 to u. So I count the number of particles in this interval. So, and the analog of law of large number just will give us, if I divide the number of particles by u, they tend to some fixed number. So this here also you can see the dependence on time t. And moreover, you can say how fast we approach the expected value. And we get the result that analog of central limit theorem takes place, so that the number of particles on interval 0u is close to its expectation, and if you normalize with square root of u, you will have in the limit Gaussian distribution with some fixed variance, and here also in form of variance you can see the how it depends on our time t. So for example, for small t, the variance here will be huge, and it behaves like 1 over square root of t. So this is all for my lectures, and so here I just wanted to illustrate you how you can use methods of point processes to try to, first of all, what we did in the previous lecture, we see how we can try to model systems that repel or attract one another, like the point has attraction or repelling properties. And today we saw how we can use point processes in order to analyze some system of particles that interact in a such way that they are or coalesce or annihilate. So that's all for my lectures, and if you have questions, or maybe you want to work together on this question, you can find me and ask more questions for details. Please, you're very much welcome to do that. Okay, for today, that's all.